Uh, this is the part 2 of the lecture on instrument transformers. We did introduce just basic contrast. We talked about the transformer basic principles, and we also looked at the voltage transformer and the current transformer. And then we looked at the specifications on current transformers based on the application, whether it is a metering application or a protection class application. And we went through that. And here we will continue with that, and then we will look at what happens if there is a DC offset and if the CT saturates, and how long does it take to saturate, or how long will it remain in saturation, which is very important for us when we get into the protection aspects, when we are trying to see how the relays behave or how the relay principles are used based on how the CT performs during fault conditions. So here is CT's calculator, saturation calculator, which is available freely from IEEE Power Systems Relaying Committee website. They have published reports. Please go there and then look for CT sat calculator. Download this Excel spreadsheet. Then you can look at it by entering the values which is specific to your application. So now let's look at this. If I click on this, then we go to the CT saturation calculator website, and you have some entries to be made here. First one is you have a linear CT current at, and then we talked about knee point. After that, it starts to saturate, and then you have a slope at which, at the rate at which it saturates. That is the slope, and this number is 122 is based on that. This is a very typical number. We can leave it as it is, or you can go back and then get the excitation curve from the manufacturer and then enter the value of what you think is the right one. And then if you look at the second one, that is your C rating of the transformer, of the current transformer. I've got a C400 here as an example, and a 1205 CT I am taking this. And then I put in here 400 volts. That is what we need. And then it is a 1200 to 5. The primary turn is 1. So the secondary number of turns is 240. And then it has got a winding resistance. Now we said that we typically assume 0.002, but this is specified, or this is already furnished by the manufacturer. And if you look at the excitation curve, they also provide you the resistance of the winding. So as number of volts as ohms per turn, and if you assume 0.002 ohms per turn multiplied by 240 provides me with a number resistance of the winding as 0.48. Then I have got a burden which could be just cable resistance, and which I said if you use a 10 gauge wire, it is 1 ohm per 1,000 feet, or 1.2 per 1,000 feet, if depending on what is the temperature of the cable. Then here I have assumed 1,000 feet or 4 ohms as the burden here. And then the reactive burden is also asking if you are using coils or electromechanical relays, it has got a reactive burden. You can enter that, but most of the times cables are resistive, and then microprocessor based relays have negligible VA. Negligible resistive burden, and mostly it is limited by the cable. So we'll just put this as 0 for our application purposes here. Then X over R, as I mentioned, that this is a system. If you have a fault, if you create a fault on the system, and if you look at the current of the fault, the angle of the fault current, and see how much it lacks the voltage, and if you take the tangent of that, that is the X over R here. So I can put this as 17, and then I'm assuming 87 degrees or 87 degrees. You can look at it. Tangent of some angle gives me 17. I took this because most of the breakers are sometimes rated at an X over R of 17. Then you are assuming that the current waveform is fully offset. This is the worst case scenario. As protection engineers, we try to see what would happen under worst case scenario. So you're fully offset. and I'm assuming that there is no remnants in the magnetic core. If I assume 0.3 remnants here, then it saturates much faster. If you look at that, let us go back and put this as 0, and you see here it changes based on that. So if there is no remnants, it takes a little longer time for the CT to saturate. And then I am assuming that the fault current, the CT was rated for 1200 to 5, and I'm assuming a fault current of 12,000 amps. Suppose if I put 24,000 amps here, you can see that the CT saturates much faster and tries to come out of it a little longer. So let's go back and put this as 12,000 amps and leave it there. And then if you look at this curve, you have got the blue one, which is ideal, the primary side current, which is scaled down to the secondary by just the ratio. So now that is a fully offset sinusoidal waveform which is going through the system, and then that is reproduced on the secondary side by the current transformer, which is a 1200 to 500 C400 transformer. You see here that the CT saturates after some time, and it remains in saturation and slowly comes out of saturation as the DC dies down. The key point which you need to take from here is that CT does not saturate at time t equals 0, and also CT comes out of saturation at infinite time after few cycles. I should not say infinity here. So let's close this and go back here, and then we know that from this you can easily look at your application depending on the fault current and XOR ratio of the system, and then what type of CT you're using. So the maximum, so when you want to select a CT, you have to see the maximum continuous primary rating of the current, and the rating factors you can use for emergencies, as I mentioned, for the transformer, and then determine the burden add cable or connected impedance, and you calculate. As I mentioned here, the voltage you try to multiply with 1 plus XOR. The reason for this is that you are actually looking at the flux inside that. So that is why you are using the same class C rating. To avoid saturation, we have to make sure that this voltage C class is greater than 1 plus XOR times the secondary current times the burden, right? Now, if you take a C800, sometimes it is not possible for you to get a, it's not possible to avoid saturation. Let's look at an example. I think there was there. Yeah, let's look at that. It will come later. The other factor you have to make sure is that you have selected an appropriate CT ratio so that the secondary current does not exceed the maximum microprocessor relay A to D limit. Some of them had 100 amps peak. Now you can get relays which are much higher than this, but that was a limit. So it cannot differentiate whether it's 100 amps or 200 amps if it is more than 100 amperes. And then will the CT always saturate? If you look at a higher XOR ratio, there is mostly likely it is going to saturate. But will it remain saturated for a long time? No. It will come out of saturation. And also it does not saturate at time t equals 0. These are two key important points which you have to use when we go through other protection schemes. We will see how the relays make use of this to determine whether the CT is saturating or not. Okay. A majority of the faults are single line to ground faults in the system. And then if there is a failure of an insulator, then it flashes over. And most of the times, the flashing over is occurring when the voltage is at the peak. And also, the DC offset is maximum when the theta minus phi. Theta is the angle of incidence of the fault, and phi is the system angle is 90 degrees. So now that because that DC term, decaying term, exponential term gets multiplied by sine of this theta minus phi. And then system angle is around 70 to 85. So fault should occur, if you look at it, around current voltage when it is passing through 0. And most of the times if it is flashing over because of a contamination, the voltage has reached some voltage must be at almost at the peak. So generally it does not, you don't have a DC offset if it is just a flashover due to insulation contamination. But if you have a lightning, which is you don't know when lightning hits at that particular phase, you don't know at what time, you will definitely get offsets under such conditions when it flashes over there. And if it is a multi-phase faults, there is a likelihood that you get these offsets on any one other voltages. And the best way is to use the CT saturation calculator and determine how the CT performs. There are other types of CTs called linear couplers, where you have an air core, just a coil, and then it goes through that, and then it produces, induces a voltage on another coil, where that voltage is proportional to the current going through the primary, linear coupler, and then we make use of that, and then there's one relay available based on this. The advantage of this is because it is an air core, it never saturates, so you don't have any issues with the DC offset. Further reading, you can look at Mason's chapter 7 and 8, but this was written at a time when the IEEE was called ASA, American Standards Association at the time, and then instead of ANSI. So they have ASA ratings there, and for classifications of C and T ratings. Then you can also look at Network Protection and Automation Guide, which would probably shed light on more IEC definitions. That's chapter 6. There are several books available. One by Mr. Stan Zokol, who was a pioneer in looking at CTs, and he was an expert. He has got a small book, concise book, which is published by Schweitzer Engineering Lab. You can go there and look at that. You can search for that. And then there is a working group in 1977 which gave equations on how long a CT takes to saturate. But now we have an Excel spreadsheet that gives you a much better idea. The picture is worth 1,000 words, more than 1,000 words, I should say. Then there are excellent books, Arthur Wright's book on current transformers and Jenkins' book on instrument transformers, which covers both voltage and current transformers. And then we have IEEE documents listed for your reference. Please go through. If you need to learn more about it, please go through and use it. Okay. As I mentioned, CT rating is always use the maximum continuous flowing through the CT, and then make sure that you have adequate burden rating to push fault current through your burden. Then you have to look at the effect of tapping the CT to a lower ratio. You can use the full rating, but you wanted to use a lower ratio here, and then here you are given different. A 2000 to 5 CT can be tapped down as low as 300 to 5. And then rating factor, if we looked at it before, if you tap it too low, then your rating factor also comes down effectively. And then now we look at the C ratings. If you have a transformer here, 800 volts is the full voltage that can be developed across the full winding. Now, if you use 100 turns only, then it's only 1/4 of the full winding. So it is essentially cannot develop more than 200 volts. It cannot. The manufacturer cannot guarantee that. Similarly, for the other side, which is 600 turns, 300 turns instead of 400 turns. 300 turns gives me 300 times 5, 1500 to 5, and then under such conditions I can go only up to 600 volts. Okay, so the CD rating also comes down, as well as the rating factor comes down if you go too low on the, if you go low, if you use lower ratios other than the full ratio. Okay, now we will go to the other one in the input to the relay, which was the voltage input. So we use the potential transformer to step down the voltage to 120 volts or less, and then C5713 again specifies the ratings. And then here you have metering accuracy, you have 0.3, 0.6, 1.2. You don't have a protection class or a metering class like in CTs. Here the voltage is going from 90% to 110%. So the ratio of the voltage is within 3%, the error cannot exceed 0.3 or 0.6 or 1.2% if the voltage is within the 90, within plus minus 10% of the nominal. Okay, and there is a special class 0.15% available, and that is published as a special standard, special document in IEEE. Voltage transformers are normally connected face to ground at higher voltages. You can have at 13.8 connected across face to face, but at very higher voltages, they typically connected face to ground. And the standard ratios as per table 12, they have given this. And then most of the relays use 67 volts, which was tapped winding on the secondary. And then the full tap normally gave about 110 to 115 volts. And that was used for metering, and then the relays used a tap voltage which was 67 volts. Most of the electromechanical relays could not take current voltages more than this, but the modern relays now can go as high as 300 volts. Here though I have specified it as 150, now I know that it can go as high as 300 volts. And the potential transformer and the regular transformer, what is the difference? You are reducing the voltage from a very high value to 66 volts. Let's take an example of 230 kV. The phase to ground voltage is 230 divided by phase to by square root of 3. And 230 or 115, these are all specific, typically these are all phase to phase voltages as defined in the standard for a three-phase system. And the phase to ground voltage is phase to phase divided by square root of 3. So it is 132,000 volts for a 230 kV system, and that is reduced, that is stepped down to 66 volts. So the ratio is 2,000. They are very high ratio, and then unlike power transformers, they have got one or two ratio levels. They're 115 to 69, or 345 to 115, or 230 or 69, and then you don't, or 69 to 13.8 or much lower voltages. It doesn't go like 2,000 or 3,000 as we see in potential transformers. And then these voltage transformers or potential transformers, I keep on interchanging these terms, they are the same. And the designations of voltage transformers are W to ZZ, and these are based on the burden, that is voltage times the current on the secondary side, which is 12.5 to 400. Okay, and you also have now 1000 volt VA available. Similarly, the polarity is just like current transformers. You have H1 and the H2. I have not shown this as it is a ground here, and it's not H1 to H2, H1 to ground. If H1 is more positive with respect to ground, and X1 to will be more positive with respect to X3. So the voltage across H1 to ground will be in phase with the voltage across X1 to X3. And similarly, I have another winding here. Now the cost of the electromechanical for the wound transformers is very high. It increases quite a lot as we keep on going up in the voltage. So at higher voltages, 69 kV and higher, we try to use a more economical version of stepping down this voltage. This is done by a capacitor voltage divider, and then at the midpoint this voltage will be about 15 to 18 kV, and the higher voltage can go as high as 800 kV, 1100, whatever we are using here. So if the higher the voltage, you have different capacitor stacks here. For this is for 69 you use one here, for 115 you will have one more on the top of this, and then you continue for higher voltages. You keep on adding extra insulator capacitors on the top of each other. And this 15 kV is now stepped down to 66 or 110 or 69 to 115 volts on the secondary side. And because you have a capacitor and an inductor, you will have a phase shift on this voltage. You ideally want this voltage to be in phase with the primary voltage. So you put a reactor here and tune it with the capacitance, parallel capacitance value, and then so that it almost becomes a perfectly tuned circuit for 60 Hertz, and it provides the same, so there is no phase shift between the secondary voltage and the primary. But disadvantage of using capacitance is it has the stored energy. So whenever a fault occurs, the voltage suddenly does not become zero. The transient response of a CCVT is effective. It is not, if it is a 60 hertz signal, suddenly the voltage goes from 100% to zero if there is a short on the top. The secondary side of the voltage transformer sees a decay as shown here. It depends on the burden of amount of load connected on the CCVT. Higher the load connected, you have got more oscillations here. So this is shown here, and then what it does is you have got a sinusoidal voltage and a sinusoidal current. If the voltage is not sinusoidal, it's a decaying quantity, and then if the current is very high, which is still reproduced very well by the current transformer, you might have a wrong direction detection or wrong impedance measurement on the side. So it has effect on transmission line relays. So you have measures, you know how this performs, and take corrective actions. Okay. So now, as we know, we looked at the instrument transformers, current transformers, and voltage transformers. We know how they behave under steady state conditions. We know how they behave under transient conditions. So accordingly, we want to make sure that relays are either designed to account for these transient performances and to take into account these errors introduced by the CT and the CCVT under transient conditions, and we take care of adjusting it so that the relay does not misoperate. What it means is you don't want unnecessary tripping in the system, so you adjust it accordingly. Then, as I mentioned here, the load higher, if it is higher, the transients are higher, and fault point on the voltage waveform also has a significant effect on the relay. I think we covered pretty much everything. As just a recap, what we did on the instrument transformers was that we know the two inputs that are given to the relay are voltage and current, and then we looked at the current transformers, and then we reviewed the classifications of the current transformers, whether it is a metering type of based on the application. So if it is used for metering, our range of interest is up to full load current only, and if it is used for protection class, then it is at the fault current levels, which are much higher than your normal metering range. So if it is 2000 amps CT, then we were interested from 0 to 2000 amps for metering purposes. And if it is a protection, and if the fault current is around 20,000 amps, we are more interested in the behavior of the current transformer at 20,000. And then we went through the standards, how they specify how to specify a metering class CT and how to specify a protection class CT. We looked through that, and then we also looked at the C rating, which is typically used for protection class in United States, and then they have similar TPX, TPY, TPS, and also like 5P20 we covered for IEEE specifications also. Okay, and then we looked at how depending on the burden, how the CT the performance changes, and then we used the Excel spreadsheet that has been provided by that is available freely on IEEE Power System Relaying Committee website, and we tried to see how the CT saturates. The two key points which we took out of that was that the CT never saturates at time t equals 0 plus. And then it comes out of saturation after some time. We make use of this in the operating principles of the relays to determine whether the CT saturation has occurred or not. And then we went into voltage transformers. We specified how the voltage transformers are classified, and based on the burden, they have got different rate classifications. And then we also looked at capacitor coupled voltage transformers. And there, and then if it is a mount PT, then if there is a short on the primary side, there is not much stored energy. The voltage also faithfully follows on the secondary side. If you use a capacitive CCVT, then if there is a short on the primary side, because of stored energy in the capacitor, it oscillates and it decays slowly, and providing generating issues on performance of relays under transient conditions, especially the lines protecting transmission lines. So we with this we have covered pretty much everything about instrument transformers, and then we will see how these affect the performance of the relays when we go through individual protection schemes.